Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you. My name is Victor. She's right. I did pick up a new role. I'm the director of this new center that we are starting in Microsoft Research. It's relatively new. It was announced on March 1st, and okay. Before this, I used to head up networking research at Microsoft for many years, and just the fact. Took on this new role because of the growing importance of mobile and cloud computing. So today I'll talk a little bit. It's a little bit of a different talk than the ones that you're used to listening to here. I'm not going to get too deep into sort of the software programming aspects, although I will give you some flavor of it. But I want to share with you a little bit of some thoughts about one of the small things we are doing in this new center. So, when we think about mobile computing, this slide, everybody sort of knows by now. And the interesting thing about this slide is that, we have got lots of limitations, even though the phone is very powerful, wireless is not very good, and then battery is not very good. But this slide could have been there 15 years ago, and it would have held true. This slide is here today, and it's true. So the question is, 15 years from now, there was, Judith had this panel yesterday about 20 years from now, and I was thinking, hey, 15 years from now, would we still be saying this? Will mobility still be sort of an issue? Because it is true that wireless is going to remain uncertain. Laws of physics, energy doesn't get better. The more you pack energy into a device, it becomes a bomb. And computations on the phone are always going to be less than what you can do somewhere else. So the question is, how do we deal with this situation? Another thing that people don't usually talk about in the context of mobility is the attention span. And as you notice, individuals, we always are doing context switching, but we're doing multiple things at the time when we use the phone. Now, what that means is that this attention span is not changing at all over the course of many years. And what we just do is we expect the system to just do its thing right away when we need the answer. And so which means you need to answer, you need to do a lot of things in the background for it to be productive. Now, there are many technologies that we've been working on, not in the mobile space, but in the sort of the desktop and space and computing space that can be brought to bear, but we can't actually use them on the phone today. So what we have today, even though it's explosive and everybody loves it, but if you look at the apps that are being delivered, they're pretty simple, right? They're not really computation intensive. But as you get more and more used to, you're going to need more of those things. And how do we get there? I talked about the battery trends. Just to put it in perspective, there's just a graph, we sort of just generated just as a fun thing. And during the time when the battery sort of went up this much, CPU went up by a factor of 246x. So there's no sort of real silver bullet out there that we can sort of say that this is going to happen. So now that leads to the kinds of applications, right? So you've seen a lot of videos, and you've seen, well, if you've downloaded YouTube, you've seen things like augmented reality there, seen interactive 3D gaming. All of this requires all the three things that I talked about. It requires energy, it requires CPU, and it requires connectivity. And so it's not necessarily easy, but we want to get there, right? It's the storage in the phone at this point, yeah. So then, it becomes quite obvious that can we combine sort of the phone, which is ubiquitously available, to the infrastructure, which is the cloud, which has got limitless possibilities. Now, if we do that, and if we do that really well, then potentially we could get there. So what the vision is, in just one line, is to enable mobile application developers to fully realize the potential of the cloud, and to do so very quickly, reliably, and easily. Now, there are three pieces of work, large pieces of work that we're doing. Actually, there are a lot more than three, but I just sort of chose to do 3, and then even as I wrote this slide, I thought I'm not even going to get to the third one. So we just focus on the first 2, and I'll tell you a little bit about each. So first is the service composition, which Judith was referring to as Hawaii. The other one is dynamic offloading of computations. So the service composition work is actually a joint effort between the Azure team, the Microsoft Research, and Windows Phone organization. And it's basically, the idea was, when we sort of started this thing, the idea was, can we integrate the cloud with the phone? And then if we do that, can we sort of try this out in universities with the next generation of programmers and see what happens? So we started off by creating an infrastructure in the cloud that will allow you to program against it with the phone, and then we basically provided all the software, and I'll get into that in a second, and all the associated materials for universities to teach courses on the subject, and so our success metrics were fairly modest in some respect. They were, could we sort of start to create new courses around this area? Can we get new applications out? Can you figure out what are the services that you need inside the cloud, given you've tried this out? And then how many students can we get trained in this new world? So what is it? It is basically, the way I sort of think about the service composition toolbox or service store or whatever is in the following manner. So if you look back many years and you think about your favorite software package, let's take something that's not Microsoft, Adobe Photoshop. If you think about Adobe Photoshop, some people got together. There was a lot of work going on in image processing, right? There were things like red eye reduction, cropping, scaling, rotating, all the other good stuff. And somebody thought, hey, let's look at these algorithms, put them together, provide some sort of an API, provide a visual GUI on top of it, and then sell it. And it was a phenomenal success, but it was still sort of niche, right? The idea here is that what if we went back and we disaggregated all that stuff, took all the algorithms, all the different things, the sophisticated stuff that people do from different domains, and create them into a service. Once we create them into a service, let's provide a composition framework which allows people to pick any service they want and put them together in any form they want. And that sort of becomes your app, and it works in the cloud, but then we provide the hooks in the phone, so you have a sort of an infrastructure to use the cloud. Okay. So basically, it led to novel applications. Why do it? I've already sort of explained that. And so we did that. We decided that we will create this service store, and these are the list of some of the services that we ended up providing. The computation and storage you already know about. That's Azure. For example, the identification you also know about. That's Windows ID. Location and notification are part of Windows Phone, for example. And then there were other services. Now, by the way, when we started this, we were not actually doing Windows notification and rendezvous notification and location at that time. We built it, and then eventually the Windows Phone organization started to ship it as well. But rendezvous and relay, matchmaking, speech-to-text, translation, video cataloging, OCR, etc., and you can keep building these services, as time permits and as you do. So, for example, a Hello World application for something like this could go like the following. This app, I'm going to actually show you a video of it in a second, was built in less than 3 hours. Most of the time was done in just doing the sort of the GUI part of it. So, here's a scenario: a Spanish person goes to visit the U.S. Street signs are all in English. Wants to convert it to Spanish. How do you do it, right? And so what's involved to build it? Well, you require an OCR service which will take the text and convert it, okay? And then you need a translation engine. That's another service. Then from a translation engine, you also need a speech synthesis engine, because you're going to take and you're going to speak it back. And you might also need all the identification and all the good stuff. So I don't know if there's a mic here, so I'm going to just use my thing here and see if this works. We don't have a mic here, do we? Yeah, it sounded like that was this. Okay, the one that was making so much noise. Straight in the front. Okay.
So here we have a sample application of a Hawaii services concept from Microsoft Research. What we have is an image translation service that's running in the cloud. We submit picture of a document or a road sign, and then that gets recognized to text, and then subsequently translated to a language of choice, and then like spoken back to the user. So presenting the correlated output of the translated text as well as the speech part of it is the important part here. So let me select a picture now. And this gets submitted to the test, and you actually see the output right away. Let's see this time with a bigger document. Here we have various passages. Let me select one from New York Times article. It's about.
So you would take a picture of this article.
Corte dice manuales no elegibles
So
para
about,
ejecutar para
Ralph
Chicago
Emanuel.
alcalde por vivir cada vez Chicago en Illinois apela a corte
And we
panel
have
uno
the
del lunes
translated
cerrado de
text
Manuel.
presented
El
here as
poner
well as
jefe de
spoken
gabinete
back.
no clasifica ejecutar para el alcalde de Chicago HS elecciones del mes próximo porque él ha no sido residiendo en la ciudad durante bastante tiempo en aparecer en la boleta electoral.
So you saw that, you basically the idea was you take a picture, send it to the cloud service, and you saw the speed with which it translated the document and came back. Now, so we built lots of services like that. One service, for example, we built was the relay service. Now here the idea was, if you want to communicate with another phone, how do you do that? And you want to sort of maybe even talk to somebody while you're doing data connectivity. Now generally it's not easy because you don't know what the IP address is, and then there's all these issues like NAT traversal and private IPs and public IPs, etc. So we built a service called the rendezvous service, which allows you to sort of hook up with whoever, as many friends as you want, and then a relay service which will allow you to communicate. Now we put the service out, and then the service was built in the context of gaming, which I'll tell you in a second about. But somebody in Singapore Management University, which was also teaching a course around Hawaii to students, went ahead and built this particular app out of this.
Hi, this is Rajesh Balan, Assistant Professor in School of Information Systems at the Singapore Management University. I'm presenting a demo application for Project Hawaii's Relay service. In this application, we have a video player that synchronizes between two different phones that are geographically dispersed. What we can see in this demo is the left phone is playing a video while the right phone is waiting because the left phone is actually playing parts of the video that the right phone has already seen. When the left phone catches up, you will see that both phones start synchronizing. At the same time, this allows people who are geographically dispersed to be able to see videos together in a shared interactive manner. They can also exchange text messages with each other, and they can also send audio chats to each other. We will now see that if you look at the display down here, you see that the left phone is 5 seconds behind the right one, and they have now caught up. And both phones are in sync, and everything is streaming through the relay service, even though the video is located somewhere on the internet. As I will show you now, you can even send voice messages to each other. This is a great video. And that concludes the demo of the relay service demo application. Thank you.
So this is exactly the point, which is that you build the services and you put them out there, and then you start to see people start to use it in very different manner. Now here's another example of another service we built, which is the matchmaking service. The idea here is that if you're into gaming, then and if you're into sort of internet gaming, you know that in order to play games, you want to be playing game with somebody who's going to have sustained connectivity to you. And in the mobile world, it becomes even harder to do that because people are moving around and wireless connectivity is not so good. So the idea is you create a matchmaking service which will then look at the latencies, for example, of the network that people are connected to. We'll look at all the other different factors that come into play and predict certain things. And so from that, it'll sort of say to you, if you want to play a game, it'll tell you these are the candidate people that you can play a game against. And so you do whatever you need to do and populate that list, and then people will play the game. So now based on that, a couple of researchers built the following thing. So this is I don't actually not a gamer myself, so I don't know too much about it. But there's a game called Light Cycles, and the way sort of it works is that you have to move around this particular space, and if you move and hit if you move to a space where somebody else has hit, its game is over. You've sort of lost it. Okay, lost the thing. So this is a video of it, and I think the video will explain what it is. Besides the sort of the running around here, I don't know if it has audio in it or not. But what they say, I don't know if they have audio, so I'll just speak. So what the researchers did is they actually took the phone and connected it to a heads-up display, and so they can see it, and then they sort of walk around in different places. But in order for this to work, it needs very fine-grained localization. It also needs the relay services because the phones are going to work with one another, and it needs sort of the matchmaking thing so you can actually play the game with it. Of course, nobody plays the game running around in this sort of fashion, but they made this work, so I thought it was kind of cute. Okay, so how do you build an Hawaii app? And here's a little plug for a Friday afternoon session. There's actually going to be a little session chaired by Judith here, which is going to talk about how you would actually build a Hawaii app. And it's kind of a fun thing because they worked pretty hard at this, and they've sort of shown that you actually built a whole app right in front of you, and then since you have the phones, you start to interact with the with the instructor, and it's kind of cute. It's actually quite good. So I want to mention how we started it. So in spring of 2010, I had two researchers visiting my group from UCS and Duke, and I was brainstorming with them, and we thought, hey, wouldn't it be fun to sort of teach courses around it? And they agreed to be the guinea pigs. We ended up teaching, three universities ended up teaching courses in spring 2010. It was remarkably successful. The professors got their rating reviews back from the students, and the students loved it because it was in the hardest field that you can be in, and they were doing all these cool stuff. So we kept up with it, and thanks to Judith, who was supporting all this effort and putting her own resources into all this stuff, this spring 2011, we had up to 20 universities signed up, and this was not without, this was without doing much of evangelization, and you will see some of the logos of the universities. And all the reports tell us that this is turning out to be really, really fun for all of them, and also fun for all of us and gratifying for all of us that it actually is something that people are really gravitating towards, and it's working. And then, the proof is in the pudding in terms of the applications. So we looked at, there's a snapshot of a bunch of applications that the students wrote. And these applications are a lot more sophisticated than anything you get in Android or even iPhone, or you get in even Windows Phone for now, because they actually are done by fairly smart people, but also uses services that are not usually available to them. So just to sort of help people along the way, we also are giving out these awards for sort of the best awards in each universities. And Imagine Cup is going to have a session on mobile cloud. So it's been a fairly successful program for us. And there's some Facebook sessions, Facebook community building stuff going on. Now, I was asked yesterday to sort of announce this as well today. So we did roll out new SDK. The new SDK has new services in it. For example, speech to text. And the big one is the optical character recognition. So now what I showed you, anybody can just implement it in whichever way you want. And this SDK is available for both the client side and the server side. You download it and you can start programming and all this stuff. It's downloaded from that website. Now, so is this enough is the question, right? And I would say it's not enough. And you probably guessed why it is. Because here are some facts, right? The facts are that the usage is going up. It's going up tremendously. The amount of data that everybody's consuming on the wireless network is also going up tremendously. And the demands of the new applications are very, very high. Now, we did some research to, that I'll come to in a second, to sort of prove this is all true. But independently, here's another graph which sort of shows how the green is where the the voice traffic is, and the yellow or yellowish bars are the data traffic. And you can see how fast they are growing on this curve. This is from Cisco, and it talks about what kind of data is actually being used more and more, and you see a lot more video being downloaded. And in the United States, at least, the FCC, for example, has been warned by many institutes that you're running out of spectrum, which means that we can speculate, we can think about all these great things we can do, but if we don't have the bandwidth to move any of the data back and forth between the cloud and the phones, we're not going to get screwed in some sense. We're not going to be able to get this done. So yeah, here's the paper that I was talking about that we did ourselves. We built this thing called the 3G test. Actually, we built it with the University of Michigan. And this graph is old. It shows 56,000 users. Actually, there's more than 100,000 users. And what we determined in today's network, no matter what your cellular provider says, there's a certain amount of throughput is the maximum you can get. And it's not good. So you can't do really interesting things. Now, for example, this is a little experiment I did in my office a while ago, admittedly. But nevertheless, it shows you what the problem is. So if you take a phone, use the Wi-Fi connection, and go to some IP address, this one, for example, belonged to some Google server, you get about 11 hops, right? You do the same thing over a 3G network, you get 25 hops. The reason is because it's not just the bandwidth of the last hop in the wireless. The cellular infrastructure is crud. I mean, it's very badly, like even the wired infrastructure of the cellular providers is very poorly constructed. And you can start to see that you're actually adding so many routes to the system before you get to the endpoint. And that adds a lot more latency than you can handle. Now, latency impacts energy. Here's a little graph which sort of shows, for example, what is in this case, on the vertical axis is time, on the horizontal axis is how much data is received. And you can see that as, and the three bars I show is if you're going over the top one is if you're going over the 3G network. The red one is going over Wi-Fi network, and this is Maui, which I'll explain in a second, which is the last one. I'll explain that sort of a solution that we've been talking to, planning on doing. And you can see sort of you match this graph with this one, and you see that if the communication cost is very large, the energy cost is very large too. And the reason for that is the radios stay up. The radios, and if you turn them up and down, even then you lose, because as soon as you turn the radio up, there's an energy spike. And so you can't really do that much. And so if you keep it up, there's, and just waiting for data to come, you're going to lose energy as well. So that drains your energy, and that's a problem as well. So working with CMU and a couple of other institutes, we proposed this idea of what we call cloudlets. Okay, the idea of cloudlets is something that is, you have the cloud, right, in the big, large data centers. You have the cell phones and things like that. And then you have an infrastructure piece, which we call the cloudlet. Okay, and then, basically it's a resource-rich infrastructure computing device which has very high-speed internet to the cloud, to the main cloud, and it's as close to the mobile device as possible. Now I'll explain to you what I mean by that. Now let's say if you were able to build a device like that or have a device like that around here, then you get better performance, right? This sort of talks about it. So that means the behavior of the application is good. There's very little latency available in the system, which will be good for energy as well. You have extended computing horsepower, and another big thing is you're not using the spectrum, the licensed spectrum, which is very difficult to get. So the instantiation of cloudlets is the Maui node. This is the Microsoft version of it. So the cloudlets concept, if you hear about it again, is sort of a jointly developed thing between us, Carnegie Mellon. There was somebody from IBM Research and somebody from AT&T Research. But Maui is sort of the instantiation of that. So the basic hardware capability is just a PC, really, and it has very high bandwidth connections to the internet. And then software capabilities that we are working on, essentially it has to be trustworthy, and you'll see why in a second. And it should be capable of handling code offloads. Okay, so where do we put something like a Maui node? Well, think about here. You've got wireless connectivity. If you're using wireless LANs, you've got, the way it works is you've got access points here. Behind the access points is a wireless switch. The access points are dumb. The wireless switch is doing all the work. Well, you take a wireless switch and you put a Maui node. You connect a PC to it. That's it. You're done. With the right software, you're done. So now you don't actually have to go anywhere. You would just sort of do a computational offload into that machine. The research questions then become for us is, what do you offload? Like, so when you're trying to use this, what parts of the application do you offload? And then how do you decide whether it should be offloaded or not? There are certain instances where offloading doesn't make sense because there is a cost associated with communications, just as there's a cost associated with batteries. Battery is used for computation and communications, and so you have to balance those two as well. If your communication channel is not very good, you don't want to be doing this because you're doing all these retransmissions. And then another one is, how do you do this without having the programmers think about all this stuff, right? So in here, everybody could do it really easily, but most of the world is not built with is not PhDs, and they just write programs. They don't want to think about any of these issues that I'm bringing up here and there. So how do we do it? And that was sort of the key to adoption, which is the simple programming model for the application writers. So so then the strategy we adopted, I don't have as much time, so I'm going to go really fast on this, and I apologize for this, but we have a paper that explains all this stuff. Is basically we use a semi-automatic approach to it. And at the highest level, the way it works is you've got some code, and what you do is you add some annotations on the code, and you say it's remotable. Now, don't worry about the fact whether you got it right or got it wrong. Just sprinkle it in a way that sort of that the programmer thinks is probably going to work, where sort of you've got self-contained codes, and you sort of add this remotable objects in there, or remotable tags in there. Now, if you get it wrong, no problems. Actually, the system will work with it. Now, one of the advantages of something like this, as you will see, is that the way we sort of built this system was, we were pretty cognizant of the fact that you may not have network connectivity all the time. So what happens then? Does the program stop working? And the answer is no, it doesn't stop working. It actually, you see a little bit of a glitch till it hits some sort of a threshold, and it decides it's not working, so it just continues to work on your machine itself. So that was one of the properties of these things. Another question that might come to you right away was, why don't you do this statically? Why do you have to do it dynamically? The answer is that actually that's actually not a good idea either, because, well, for one thing, disconnected operations don't really work very well, and there are some semantic meanings to applications too, which you have to keep in mind when you decide whether something has to be dynamically loaded or not. That becomes a real problem as well to come up with. So sorry about having all these pictures and not being able to explain it. But the big concept of this slide was really that the sort of the secret sauce, as you might call it, is this profiler and the decision engine logic, which decides whether to offload something or not. And what the profiler does, it takes some values from things that are happening constantly. For example, what is the execution time? What does the call graph look like? How many CPU cycles? It takes some modeling of the energy as input as well, and it also takes things like network latency, bandwidth optimization, and network types that you're operating on. And it sort of takes all this data, creates an ILP out of it, builds an optimization functions, decides based on that optimization function whether it needs to manage the system, it needs to execute on the device or move it out, and comes up with an answer. And so the performance looks pretty damn good. This is actually real systems that we have built, and they work. So for example, this was a face recognition system. Here's the legend. Here's when you have a smartphone with just a regular 3G connection. Here's a smartphone with a Wi-Fi connection with different latencies depending on where the MAUI node sits. And you can see quite clearly that the execution time for identifying face is quite substantially different with low latency. This is an example of energy, and it shows here, you will see this graph, which is with Wi-Fi, shows to be higher energy. The MAUI system actually did not generate this graph. We had to force it because this was a case where offloading did not make sense over Wi-Fi. Okay, I just wanted to sort of demonstrate that. But here are some of the data. For example, when you're playing games, you can go from 6 to 13 frames per second and save a lot of energy. So I'm done really quickly. So if you sort of look ahead and to think about the concept that I talked about in cloudlets and all, and you say, well, there are improvements in networking, you could argue. That's true if you have improvements in networking, but they would still be less than, for example, what a wireless LAN can give you. Okay, so you might get really, really fast cellular networks, but wireless LANs are going at multi-gigabits even today. What about hardware and storage? That's true, improvements are there. but you will never catch up to what the cloud is going to be able to provide you as well. And similarly, cognitive reasoning and all that stuff, you're always on the right side of the curve or wrong side of the curve in some sense, whichever way you look at it. So the cloudlet thing, I think, makes a lot of sense. So I guess this is my final slide that it talks about having the ability to sort of think about all these services that are in the cloud, provide the composition framework to be able to use them, and then also in certain cases offload the engine to be able to receive that. Now, if you want to sort of know a little bit more, here's the website. And if you want to think about teaching courses in Hawaii, please write to me or Judith, and we'll gladly sort of work with you to make that happen. And sorry for being fast.
Thanks.